This is a short video describing how to build a do-it-yourself hyperspectral camera. The camera is indicated here in the center of the image. It is a scanning camera and it's sweeping out the image. On the left, you can see a section of the scene that's being swept out. This red indicator shows the slit, or depicts the slit that's being scanned out. On the right, you can see a single frame that is captured at each scan position. What you can see is an image of the slit and then the spectrum that's being scanned out for that slit. We'll talk a little bit more about what all this means later. Here in the lower right, the spectrum is inserted into a data cube. You can think of the data cube as being built one slice at a time, sort of like a loaf of bread. The build was done with about $550 in parts, and structural components were printed with a 3D printer. I used a stock Ender 3 with PLA, so an expensive printer is not required. This video won't be a step-by-step description, but just show an overview of how it's done with pointers and some of the bigger pitfalls. Before getting into the build, let's talk a little about what a hyperspectral camera is. Given a scene, a conventional camera will capture a color image which consists of 3 frames, a red, green, and blue. These frames correspond to how the human eye and brain form images and respond to colors. In a hyperspectral camera, you capture many frames, and instead of frames that are useful to the human eye, the frames correspond to narrow bands of light at given wavelengths. The camera we built eventually landed on 268 bands running from around 400 to 700 nanometers. The data from a hyperspectral collect is referred to as a data cube. Instead of 3 colors per pixel, each pixel has many colors and can be plotted as a spectrum. These spectra can be used to distinguish different materials. The point of a hyperspectral camera is not to make images for humans to view, but to collect data that can distinguish different materials in the scene. Hyperspectral data has many uses. Here are some examples. Precision farming. In a regular image, if you see a patch of brown, you will think there is a problem in that vicinity. With hyperspectral data, the problem can become apparent earlier. The camera collects data which indicates distressed areas before they become visible to the human eye. Industrial inspection. The many colors make it easier to find flaws or discriminate between good and bad samples. Medical diagnosis. Diseased tissues and pathologies can exhibit a change in detailed spectral response before it becomes visible as usual color. Mineral surveying. Discriminating various minerals on the surface is easier when you can analyze spectra. To summarize the goal, we would like to build an instrument that collects a data structure we will call the data cube. The cube contains detailed spectra on each point in the scene. Each pixel is backed by a full spectrum which can be used for various discrimination tasks. This video describes how to do a DIY camera build. One comment before we continue. If you're familiar with hyperspectral, it is most common to view the data as false colored images. Those kinds of images are highly dependent on the application. We'll be pulling out individual frames and viewing them as grayscale images. Because the data for each frame is a narrow band around each wavelength, each frame is not as high contrast as you would see in a grayscale image. In particular, around 400 nanometers, the frame gets noisy because silicon is less sensitive at short wavelengths. Around 700 nanometers, the frame also gets noisy because the sensor focal plane we're using has an infrared filter. Because sunlight is brightest around 500 nanometers, you tend to get the best images there. One of the future projects would be to remove the infrared filter from the sensor plane. This would also help with plant analysis experiments, since plant analysis depends heavily on infrared. Now let's consider a conceptual version of how the camera will work. We start with a scene we want to capture. We have to capture the cube in some kind of orderly fashion, so we'll capture it one column at a time. Imagine we put up some kind of giant curtain that blocks out all light except from a single column in the scene. Obviously this is impractical, but we'll make it practical in a moment. Now put up a giant dispersing element like a prism. It will create a spectrum for each point along the column. To emphasize, each point along the column corresponds to a horizontal spectrum. We somehow collect this spectrum and it becomes a slice in the data cube, like a slice in a loaf of bread. Now we move the screen a little and repeat the measurement. The next measurement becomes the next slice of bread in our cube. Now with this in mind, we'll describe the sensor we'll build by giving an outline of the path of light through the system. We start with a scene on the left. Here's an assembly depiction of the hyperspectral camera. We'll point out components as we introduce them. In the previous slide, we notionally created a column with a curtain over the scene. This is of course impractical. Instead, we use a lens which creates an inverted image of the scene at the lens's focal plane. The lens is indicated with an arrow in the assembly. It is fairly easy to screen off a column in the reduced image with a precision optical slit. Now the inclination might be to put a dispersing element in immediately to generate the spectrum. The problem is that because of the first lens, the light is converging, so the dispersing element is going to create a mess. Instead, we add another lens, one focal length from the slit. This recollimates the light, so a dispersing element will do the job we want. Now we add a dispersing element, and instead of a prism, we'll use a diffraction grating. This is more compact and gives better dispersion. We add a third lens, which creates an image of the spectrum of each point along the slit. We have to collect the image, so we will use a CMOS sensor plane. We need to store off the images and also, as we'll see in a second, control a motor. For this, we're using a Raspberry Pi 4 computer. Recall that we need to move the slit to capture the slices of bread. We'll do this by rotating the whole camera with a stepper motor. The stepper motor is controlled by an A4988 motor control chip, which is ultimately commanded by the Raspberry Pi. Also, there are some electronics to help with the microswitches for positional calibration. This all feeds into the GPIO of the Raspberry Pi. Finally, we have a very cheap webcam that we use for viewfinding and debugging. The key challenge in a DIY camera is getting the lenses aligned. We solve this problem by using Articam lenses. We'll see why this works in a second. I got a kit of 5 from Amazon for about $110. We use a 12mm lens for the first, a 25mm lens to recollimate, and a 6mm lens for the final image formation. The key to getting everything aligned is to use CS mount lenses assembled with 3D printed parts. A CS mount lens has a fixed distance from the flange to the focal plane. This distance can be adjusted a little with lens focus, but designing around that flange distance is going to make our life easier. You can see the first 2 lenses here in the assembly. They are arranged flange end to flange end. We print a 3D assembly that separates the 2 flanges by the right amount. As we'll see in the next slide, the slit is exactly in the center. It is possible to 3D print the threads right into the part if you set the slicer to print at the highest quality. The whole thing screws together quite easily. The way we screen out the image, leaving a narrow column, is with an optical slit. We used a 40 micron by 1 centimeter slit we purchased from Thor Labs. Not sponsored, and in fact no products or vendors in this video were sponsored. It costs around $120. The slit assembly is between the first and the collimating lens. As we saw in the previous slide, we can print parts that hold the 2 lenses at exactly the right separation. We can also position the slit where we want, at the lens's focal planes. Here's where it appears in the final camera. And the 3D printed assembly is 4 parts. One that accepts the sliding cartridge containing the slit and the cartridge itself. The slit is friction fit into the cartridge. The reason I used a replaceable cartridge approach was that I thought I might want to experiment with different slits or remove the slit for testing. It ended up not being necessary, but I'd still probably do it that way again. The dispersing element was also from Thor Labs. It is a grating for around $130. You can see it here in the camera assembly. The grating assembly has 4 3D printed parts. The grating is sandwiched between 2 identical halves. Since the lenses are not threaded on the sides that are facing the grating, they are held in place using spring clips with a thumb lever release. The spectrometer section is here on the camera. The exploded assembly shows that the clips used to hold the lenses are screwed into the part that holds the grating. I avoided using glue because non-specialty glues can outgas and destroy optical components. This is especially true of acrylic glues. The 3D parts are held together with screws and friction when they are close to the optics. The 2 halves of the grating holder are held in place with 4 screws and bolts. Also notice that the grating is tilted. This is to eliminate a stray light issue. We'll discuss this again later. The camera sensor array is an Articam for the Raspberry Pi. It is based on the Sony IMX477. Since it comes with a CS mount, the final imaging lens just screws in. The computer used for capture and motor control is a Raspberry Pi 4. You can see here in the assembly and the camera where they are located. In this exploded view of the camera and computer assembly, you can see the computer enclosure and parts to support the camera. The 3D printed parts are gray. I made a mistake with the lens and left the front of it gray. That's just a mistake. No part of the lens is 3D printed. The odd-shaped unit at the top is a cheap webcam that is connected to the Raspberry Pi via USB. This is used for viewfinding and debugging. It is not part of the Hyperspectral Collect. The board on the far right is for motor control. The motor driver is an A4988. The board is just the small amount of electronics needed to run the driver and the 2 micro switches used to calibrate the scan position. The motor for scanning is depicted in this assembly. It is a cheap NEMA 17 form held between 2 printed mounts. I used a $10 motor. That was probably a mistake since the lack of torque creates some vibration, but it still works. The bottom mount has a flange that fits into my tripod. The cheapness of the tripod also didn't help with vibration. The upper mount has 2 wing-like structures that are used as stops for the microswitches. The complex printed part at the top of the assembly screws into the camera enclosure near the middle and onto the motor shaft near the rear. The part also mounts the microswitches for positional calibration. 3D printing of optomechanics and orienting lenses like we've done is not without a downside. As you can see, the optical system without support is somewhat floppy. To correct this, we made some support parts to ensure the optical system stays level. We also did this to ensure the slit and grating do not rotate, which can throw off where the spectrum gets imaged. With the camera built, we can start collecting data. Scattered light was an early problem I had to address before doing various calibrations. Here is a conventional picture looking outside of a window where I had the hyperspectral camera set up. Here is a single wavelength frame out of an early collect. All that cloudy stuff near the bottom is scattered light. In the setup, I had the grating as perpendicular to the optic axis. This causes light to bounce around inside the optics and create the mess you see. By tilting the grating by 10 degrees, the scattered light bounces out of the main optical path and you get a much cleaner image. Next, we want to calibrate the wavelengths. I used this setup. The fluorescent lamp on the left has spectral peaks at specific and known wavelengths which can be used to calibrate the sensor. The incandescent lamp on the right has a broad continuous spectrum that we can use to tune our processing. The diodes in the middle are good for sanity checks. Because of the lens setup, I was frequently turned around on what side of the image had the red or blue part of the spectrum. The diodes helped me orient myself. To calibrate the wavelengths, we use the fluorescent lamp. A fluorescent lamp has a spectrum with well-known and well-defined peaks. After a collect, we can see the spectrum, but you don't really know what we should use on the x-axis. We have indices of the column, but we need to convert it to wavelength. Using a simple linear regression model, we can map indices to wavelength. This was done with standard linear regression. Once the wavelength calibration is complete, we can check against some laser pointers. I got cheap ones and aimed the red and blue lasers at the diffusing paper on the lamps to get more of a glow. The calibration is off a little, but not a lot. Since everything is on the same scale, you can see how much brighter the green laser is than the blue, and how much brighter the blue is than the red. We got this kind of dynamic range by using a 12-bit raw collect, which we'll talk about next. When you get a color image out of a commercial camera, it has been processed. The unit in the camera that does the processing is called the image signal processor, or ISP. This processing is meant to make the picture look pretty for humans. That processing is not really what you want to do when you collect spectra. One thing the ISP does is set a brightness beyond which everything is just considered white. This leads to the saturation step you see in the graphs. Interestingly, you can seem to get different saturation levels at different wavelengths as seen in the upper graph. This is generally not acceptable, so instead we do what's called a raw collect. Cheaper cameras generally do not have this option available, but the ArtoCam unit does. In a raw collect, you get an array of red, green, and blue filtered pixels like this, called a Bayer filter. The processing is done by setting what is considered a 0 level and then converting to red, green, and blue frames with interpolation. One additional benefit with the raw collect is that a standard image generated by the ISP has 8 bits of dynamic range. A raw collect with this focal plane can be set to have 12 bits of dynamic range. This means there is a larger disparity in the brightness in the same scene. For example, we previously saw a green laser with a peak of 3,000 counts collected next to a red laser with a peak of 65 counts. Now, we don't want color, we want a measure of radiance. We can try to get that by converting the red, green, and blue frames to gray using, say, a standard linear combination. This will convert the 3 frames to a single grayscale frame. The problem is that the standard linear combination is again made for humans. The spectra of the incandescent light, which should have only one peak, looks better, but still has a problem. This is because our conversion to gray is not suitable for this application. We want to solve the problem that conversion to grayscale is not suitable for measuring spectra. The source of this problem is that conversion from red, green, blue to a single radiance measurement is not done well with the usual gray conversion. Fortunately, the vendor of the focal plane, Sony, provides a chart showing us how each of the 3 color filters respond to various wavelengths. We can use this to get a better measurement. Suppose we want to know the radiance at a particular wavelength corresponding to a particular column in the spectrum capture. The values in that column are red, green, and blue measurements, which are derived from a single radiance at a known wavelength. The values of S sub lambda for each RGB come from the vendor-supplied responsivity curves. Given this model, we want to estimate I sub lambda by minimizing the difference between the RGB we see and the RGB we expect given the responsivity. The minimization is easily computed, and we can back out an estimated radiance using a standard least squares formulation. The resulting spectrum is now consistent with the spectrum of an incandescent light. Now that we have the instrument, let's just talk about some very basic processing you can do. Here's a scene. It's not the prettiest, but it was convenient for me. Here's a single frame in the 500 nanometer region, and I've selected some areas with the same materials. If I plot an average spectrum in each of the rectangles, you'll get something like this. All the spectra look pretty much the same. The sameness is because they are all reflecting sunlight. The reflection modifies the spectrum visibly a little, but they are broadly look the same. If you look close, you can pick out differences, but it's hard to see. This is a testament to the fact that our eyes are picking out something a little different than what we see in the gross spectrum. Now the same scene with the same region selected, but we're going to do a very little processing. We ask what single spectrum best describes the whole scene, and then we amplify everything except that spectrum. Essentially, we use an SVD to find the representative spectrum, although the code is not using a call to the SVD function. We then build a projection that kills everything except the representative spectrum. Finally, we build an operator that multiplies everything but the representative spectrum by 7 and leaves the representative spectrum alone. When we do this, you can see that the different materials look visibly different. Of course, there's all kinds of processing that can be done. This is just a very small taste. So where do we go from here? The Articam has an IR filter. IR is very useful in botanical analysis, so it would be nice if it were removed. There are instructables on removing the filter, but I wanted to get a system working before potentially damaging the sensor plane. It's a little hard to see sometimes, but combining the red, green, green, blue filtered images into red, green, blue frames is somewhat noisy, especially in low signal situations. I need to spend some time improving the dBayer algorithm. In fact, I think it should be possible to compute a single radiance without an intermediate conversion to red, green, blue frames. I've done more advanced processing. If there's interest, I could put up some analyses in separate videos. The goal was to make a cheap DIY hyperspectral camera. The cost of the grading was around $130. I was initially thinking it would be possible to make it using cheap film for the spectrometer. The diffraction efficiency would be terrible, but it might be enough and cost would be way down. I used the optics grade grading just to make the build easier by removing a source of problems. I'd recommend you do that on your first build. In the spirit of reducing cost, I was hoping to build the slit from something like aluminum foil. I tried, and that didn't work too great. So again, in the interest of making my life easier, I bought an optical grade slit for around $120. I was thinking I could maybe 3D print some kind of jig that would help make a precision slit, or a more precision slit. Either that or look into some kind of chemical or electrolytic process. I don't know. I think the system is light enough to fit on a drone. On a drone, there's no need for motor or motor control since the image is swept out by vehicle motion. This is obviously ambitious, but I think it's feasible. I would like to use this system to train reconstruction on computed tomography hyperspectral imaging. CT-HSI is a hyperspectral collection method that requires no scanning and captures the image in a single shot. It would not look outwardly different from the current device. The pinhole would be replaced with a window and the grading with a computer-generated hologram. I wrote an image generation simulator to do some preliminary experiments. The big expense is the computer-generated hologram that does the dispersion. I've priced some out and they come in at over 1.2 grand. I have ideas on making that cheaper, but I might just explore simulation before investing in hardware. I have lots of notes on doing more, so I'll probably need to spend some time to hammer out what I want to do next. Well, that was all. This was a fun project. It involved optics, programming, image processing, 3D printing, 3D design, which I did with FreeCAD, motor control, minor electronics, and probably some more. It's a great way to exercise multiple DIY skills. The big ticket items for the build came out to just under $500, and I threw in another $50 for miscellaneous parts and electronics. I think $550 for your own hyperspectral camera is a pretty good deal for a system that will cost $5,000 to $20,000 off the shelf. There was nothing exotic I used. As I said, the printer was an Ender 3 used in stock setup. Except for some optical elements, most parts can be obtained from Amazon or SparkFun or Adafruit. The specialty optics came from Thor Labs, but another supplier like Edmunds or Newport will work. Give it a try, and thanks for watching.